If I have, we usually do integrals with respect to x, the integral, we've done several examples with integral with respect to x, but it doesn't matter what integral, what the variable is there. Take, for example, the integral t cubed minus 3t plus 1 dt. I'm going to do that from -1 to 2. Yeah, this variable can be just about anything. It doesn't have to be necessarily an x. So that's first point to be made on this one. I want to show you. But it's still the very same idea. To evaluate this integral, it's fairly simple. Since I've just got minuses and pluses here, that's what makes this pretty simple, and it's just power rule antiderivative, right? The antiderivative of our expression here was that 1/4 t to the 4th be minus 3/2 t squared, right? Because we're adding 1 to these powers. And then we've got 1, so that would just be t. And again, the plus c is not necessary on these. Now we'll do a couple here later where that plus c, we'll have to throw that in. But for these definite integrals where you've got the upper and lower limits, you don't need the plus c. But then, yeah, let's do that for our limits there, which means plug in the 2 first. So it'd be 1/4 2 to the 4th minus 3/2 2 squared plus 2. And then subtract what the expression is evaluated at -1. 1/4 times -1 to the 4th minus 3/2 -1 squared plus -1. That's what this will come out being. It's 1/4 of 16, which is 4. 3/2 of 4, which would be 6. Minus 6, and then plus 2, and then these will be, -1/4. -1 to the 4th is positive 1, so that'll just be 1/4. -1 squared is positive 1, so that'll just be minus 3/2 minus 1. Oh, look at that. All that cancels, but what have we got here? I should do that in my head, but it's, so negative 1/4. 2.25, 2 1/4, or was that 9/4? They probably in the book would list it as 9/4, but I'm okay with those other decimal equivalents too. So yeah, doesn't really matter this variable here. Now let's graph the function. And how do they say it? Interpret the integral from part B here. Yeah, so let's graph this. Of course, we've got t's instead of x's, but when we graph it, we would probably most calculators use the x's. And what we get it looking like anyway is something like this. All right, so it goes up. -1, we're up here at 3. Here. Something there and something there. Get pretty close anyway. All right. So that's our graph. So technically, I guess it's t cubed minus 3t plus 1. Or this would be the t-axis instead of x. But anyway, what we're talking about then for this integral, the integral then is, what we know is that it's between the curve and the x-axis, that area that we're talking about. So in this case, we're going from -1 to +2, so it'd be -1, +2, so we slipped over a little bit there. Yeah, it's between the curve and the x-axis, so it'd be this area here. And then since we're going all the way over to 2, it'd be this area here. And then there's a little bit, because it goes just above the x-axis there. And so that, we're talking about that area. And again, it's not necessarily a total area because depends on your definition of total, but probably a better way to think of it is a net area, right? Because this area here is positive, this area is below the x-axis, so it'd be a negative, and then you've got another little positive sliver right there. And so what we're talking about, the integral is it's that net area between the curve and the x-axis. We don't want to lose sight of what we're actually computing here when we find it. So net result is it's about 2 1/4 area-wise right there when we all is said and done. All right. Now this one, I want to mention this one. So I don't think we've done one officially. You may have had one. Come across one of these already, but so again, we can do integration with respect to y. That's fine. It's still same thing, but for purposes of antiderivative here, we probably want to write these as y to power. Square root of y is y to the 1/2, and then minus 3 over y squared, that's 3 times y to the -2. Yeah, writing those as powers of y, or powers of x, or powers of t, or whatever, that's much preferred when we go to antiderivative, right? Because then you just use the power rule. So write them like that, and then we can, since it is subtraction, we can do our antiderivative thing for both of those separately. Let's see, so the antiderivative, you got y to the 1/2, you add 1, so that'd be 3/2, 2 plus 2, I mean 2 plus 2 over 2. And then, yeah, that would mean multiply by the reciprocal up front. Then here, if I add 1 there, that's a -1 power, so I would divide by -1 for that part. And then evaluate that and our limits, which is going to give me 2/3. That'd be 9 to the 3/2. Minus make a plus. 3 times 9 is -1, minus, and then plug in the 2/3, plug in the y to be 4. So it'd be 4 to the 3/2 plus 3 times 4 to -1. And you can punch that in your calculator. I like to think about what these would be. 3/2 power, you got the square root, right? Divide by 2 would be the square. So you got the square root of 9, which is 3, and then that's cubed, so it'll be 27. 9 to the -1 is, that'd be 1/9. Over here we have 2/3. That'd be the square root of square root of 4, which is 2, cubed, which would be 8. And that'd be 3 times 1 over +4. But anyway, just punch them in your calculator. It'll do it all for you. All right, so we got 2/3 of 27, which is 15, I guess. Plus 3 times 1/9 would be 1/3. Minus then 2/3 of 8 times 8, and then minus 3/4. Anyway, all told, it's 13.75, or fraction, that's probably what the book will give us, 55/4. Even one, perfectly fine. All right, any question or concern there? Now again, just to emphasize here that the integral a to b f of x plus g of x dx, we can do the antiderivative for that, and however we want to write it, big F, little g, or big G. So yeah, we can do antiderivative of that plus antiderivative of that, and then evaluate that from a to b, kind of using our other notation here. You can do the same thing for minus. Just do that. Okay? That's good. That's fine. Not so good, though, this. In general, that does not equal antiderivative times antiderivative. Not good. Okay. This, when we get a multiplication in an integral, things get complicated a lot of times. Now, sometimes not so much, but sometimes it gets complicated. And we'll talk a lot about multiplying. Well, we talk a lot more about it. We talk a lot more about it in second calculus for us anyway. But we'll talk a lot more about it though in the future here. Same thing on divide. Cannot do that, where you take the antiderivative of f divided by the antiderivative of g, no go. Usually not going to work. Okay? So, I mean, we've said it a couple of ways now, but just to emphasize that. So, what do we do? One thing we can do when we have multiply is this. So let's say we've got negative 2 to 4 x times x cubed minus 7x minus 2 dx. Now, one thing we can do when we have multiply, what we can't do is the antiderivative of that times the antiderivative of that. Just doesn't work out. But what you can do, if you've got a multiplication where you can actually do the multiplication, then that's probably the way you want to go about it, because other alternatives are not quite as nice. So what I'm saying is get rid of the multiplication by just going distributing in this case, or if you have to FOIL or whatever, go ahead and do that, and then that'll take care of that. So it'll be x to the 4th minus 7x squared minus 2x dx. So you don't have the multiplication now. All we have is the subtraction, and subtraction we can do all day long there. It's is that 1/5 x to the 5th minus 7/3 x cubed. That'd be x squared. So it'd be 2 divided by 2. Yeah. Then we got it. Let's see, that'd be 1/5 times 4 to the 5th minus 7/3. It's 4 cubed minus 4 squared, because that'll just be 1's there. And then minus, plug in the 2. And what do we get? 1/5 times 1,024 minus 7/3 times 64 minus 16. That'll be 1/5 times -32 minus 7/3 times -8 minus 4. So anyway, whatever those turn out to give you. Yeah. I get here, it's a long minute. Fifth, no, 4, 31.2, or get that as a fraction. 156 over 5. Okay? All right. Now, what about this one? Now, when you get denominators involved, wherever they are involved, one thing you have to be careful with, remember, was the continuity thing. We talked about this last time. This one's okay. From these limits would be okay. If I did this for the way we've talked about so far, this one, well, that would be a bit more of a problem. We can do it other ways. We'll talk about in the future. Why would that one not be so nice, I guess you might say? Well, it's because, again, you got denominator 0 at 0, right? And that would be included in the endpoints, or the limits. And so that one we couldn't do. We haven't talked about how to do that yet. That would be a whole another discussion. Here, though, we're okay because we didn't include the 0. Those limits include the 0, so that's a bit of a problem. But here, the problem here on this one is not that, but it's dividing. And like we just said, when you have dividing, it's not antiderivative divided by antiderivative. Well, again, like we talked about with the multiplication over there, if we can get rid of the dividing, so to speak, then we're in better shape. In this case, we can because, well, one thing we can do is go ahead and divide both of those, divide the x squared into both of those, and that'll make it 1 to 3 x squared minus 3x to the minus 2, right? And now we don't have that little problem of dividing. We can just do the antiderivative thing. That's 1/3 x cubed minus 3. Again, we got x minus 1, so we had that one earlier. All right. So that's 1/3 of 27. Again, plus 3, 3 to the negative 1. Then minus plugging the 1. 1 cubed is 1, so it'd be 1/3 plus 1 to the negative 1 is 1. So it's just both cases 1. So what do we get? 9, that'd be 1, minus 1/3 plus 3. Anyway, 10 minus 3 1/3. Yeah, it's 6.6 repeating, or 20 thirds. All right? Good with that? Any question, concern on that?